Okay, there we go. Okay, so yeah, as I said, thank you, Tim, for the great introduction. Much appreciated. So, like I said, this evening I'll be taking you through some of the specifics of the Harry DeWolf class, the newest addition to the Canadian Navy's fleet, and her Arctic and ice trials, which I was lucky enough to be a part of this past year. So, a little bit about myself. As Tim mentioned, I grew up in Newfoundland, moved to St. John's, Newfoundland in 2012 and started my Bachelor in Mechanical Engineering at Memorial University. Spent some work terms there. I got some work experience, like Tim mentioned, with Suncor Energy. Also spent some time with Nalcor Energy on the Muskrat Falls hydroelectric project, and then was able to graduate in 2017 and start the hunt for a job. So I was initially looking for the offshore oil and gas industry. Didn't turn out so lucky with that. The industry was in a bit of a downturn. Growing up in Newfoundland, I spent a lot of time with my grandfather out on the water fishing. He spent a lot of time building boats, working on his boats, and I spent a lot of time with him doing that. So I saw a posting for Irving Shipbuilding. Thought it'd be great to give that a try. So I applied and was lucky enough to start with Irving in July of 2017. So when I started with Irving, I was able to take advantage of a training program that they were putting new graduates through. So I got some exposure within the engineering departments, the planning departments, and then my final part of that little rotation was with the test and trials commissioning team. So I've been with the test and trials team on the AUPS project now for just over 2 years out of my 4 years with Irving, and I've loved every bit of it. It gives me an opportunity to be hands-on with the vessel, commission the ship, hand it over to the Navy, and train the Navy's crew for Harry DeWolf, and then sail with them for post-acceptance trials. So great experience and exposure there, and looking forward to what else is to come. So a little overview here of my experience on the Harry DeWolf class. So I was part of Builders Trials back in November of 2019. Then afterwards, we conducted Harry DeWolf Sea Trials in February of 2020. We also then did the pre-delivery sea trials and crew training exercises in June 2020, where we would take ship's crew, engineers, master sailors, and below through all the specific auxiliary systems on the ship that I had an expertise in. I was able to educate them and provide specifics on the systems and how they expect to operate them. After delivery of Harry DeWolf in July of 2020, we then conducted some post-delivery support and further crew training into October. And then in 2021, I was able, along with a few other members of Irving Shipbuilding, to take part in the Arctic and ice-breaking trials as the post-acceptance trials with Harry DeWolf, with her crew, and with the Royal Canadian Navy. Since then, we've successfully conducted sea trials in the future HMCS Margaret Brooke in May of this past year. Great set of sea trials there. We have a great picture of her in that bottom right there, coming back from sea trials just last month. That was a great success as well, and we're looking forward to delivering her to our Royal Canadian Navy in the near future. So just a quick outline on how I'm going to conduct and present the details for this evening. So I'll start out with a quick overview of Irving Shipbuilding itself, some of the projects or facilities, things that we're working on as part of the National Shipbuilding Strategy. And then we'll get into specifics on the Harry DeWolf class vessels, take a look at what the platform is built for, what it's designed for, and as well some specifics of the interior of the vessel. And then we'll dive into the details of the Arctic and ice-breaking trials conducted in February this year. And then we'll clue things up with just some final thoughts about Harry DeWolf, Irving Shipbuilding, and the National Shipbuilding Strategy. And then as well, we'll lead into an open Q&A session to be able to have a good discussion and answer any questions that you may have. So starting out, Irving Shipbuilding, just a quick overview on where we are as a company and as a shipyard in June of this year. So right now, we've been building and fabricating modules for almost 50 years at the shipyard. We offer facility services, construction and repair, engineering as well as technical services, and then industrial modules and fabrication. So we have a number of facilities. We have obviously the Halifax Shipyard, Woodside Industries and Marine Fabricators, both located in Dartmouth, Nova Scotia. And then we also have Shelburne Ship Repair down on the southern shore of Nova Scotia, and as well various fleetway offices for engineering and contract support. So the shipyard itself, considered North America's most modern shipyard. So we've had over $400 million invested in it. It's the largest undercover shipbuilding facility in North America. And that's in the picture on the left there. I'm sure many of you are familiar with that building, that property. That's where we assemble all the modules, the blocks, the mega blocks for the Harry DeWolf class ships, and then transfer them out to land level in the right of that picture. And then from there, we join the mega blocks together, launch the ship, get her in the water, and then start the final touches to construction and lead into the commissioning and sea trials program prior to sailing her down the harbor just a bit to our Royal Canadian Navy customer. And then on the right, we also have Marine Fabricators. So that's where all the raw steel material over in Dartmouth arrives. They kit that steel based on the fabrication of the module that we're going to build at the shipyard, and then truck that across from Dartmouth to Halifax, and then we're able to start assembling that into the units and the joins and the mega blocks to form the AOPS platform. Some other shipbuilding locations: Woodside Industries, also in Dartmouth. That's where we construct some of the more complicated units of AOPS, such as the bow region with its ice breaking belt and the bow thruster, and there's a lot of complicated steel work in that area. I've also mentioned we have Shelburne Ship Repair Facility on the southern coast of Nova Scotia, currently housing the Canadian Coast Guard ship, the Copet Hobson 1752, the former Edward Cornwallis, which is going through a midlife refit there as well. And then our most recent location is the Blue Nose building in Dartmouth, and that's where we have our Fleetway and CSC team. And we've got nearly 600 people working there now for the engineering and design work that's ongoing on the CSC project. An overview of AOPS itself. So AOPS 1, HMCS Harry DeWolf. Like I said, we conducted builders trials in November 2019, sea trials in 2020, and then delivered her last July to the Royal Canadian Navy. Future HMCS Margaret Brooke, AOPS number 2. She's been through sea trials in May 2021. And like I said, we're looking forward to delivering her in the second quarter of 2021 in the very near future. And then we have AOPS 3, future HMCS Max Bernays. We have all the 3 mega blocks now currently joined and assembled at the land level facility of the shipyard, and we're working towards launching her in the fourth quarter of this year. And then into AOPS 4 and 5. So AOPS 4, the future HMCS William Hull. Construction has begun April 2019, and we've had a keel laying ceremony for her in February 2021. And just last month, we cut the first steel for AOPS 5, the HMCS Frederick Roulette. So production is, very much underway on the AOPS class vessels, and we're working towards delivering them to our Navy. And leading into AOPS Ship 7 and 8. So we had those 2 ships announced by our Prime Minister to supply those to our Canadian Coast Guard. So a great platform, I think, for our Canadian Coast Guard. It's going to be, they're doing upgrades to deck equipment, upgrades to facilities for science and research on board, and it's just going to be, a really, really great versatile platform to serve for our Canadian Coast Guard. And it's going to be a great vessel leading up to that. That's going to be proven by our Navy. So right now, preliminary design review is underway, and then we'll lead into the final design review to follow. Then, of course, at the shipyard, we have our Halifax class maintenance. So the Charlottetown finished her docking work period in March of this year. And then we've began the docking work period on the HMCS Ville de Quebec on the 31st of March this year. We've also invested about $3 million into a new pump house facility. So it's great to see, those funds and that money being invested into, the dry dock's been a part of the Halifax area for a very, very long time. So it's great to see that still being utilized to serve and service our fleet. So it's great that we're able to put that money into that and keep that as part of the Halifax Harbor. And as I mentioned, in Shelburne Ship Repair, currently 70 plus employees with just a stern view there, the Canadian Coast Guard ship for the Copit Hobson 1752. The HMCS Glace Bay has also arrived in April 2021 for some work, and the CSS Acadia arrives June of this year. Other things that we're able to do at the shipyard as part of the National Shipbuilding Strategy. So we're growing Canada's next generation of shipbuilders. So since 2016, we've had over 2,000 positions filled and working on the IAPS program. Almost 300 of those filled during 2020, during the COVID-19 pandemic. We've had over 200 apprentices, a number of which are achieving the Red Seal status last year. And we have an in-house trades academy with a number of instructors and trade courses to help build our workforce. And then we also have training and development opportunities across the shipyard. Like I said, I was able to take part of lots of training opportunities right out of the university at the shipyard to grow my exposure and my experience within the shipbuilding industry and be part of the commissioning team for the Harry DeWolf class right now. So also for workforce development, we're working with African Canadians, we're working with Women Unlimited Partnership, Indigenous Canadians, and veterans as well. So we have lots of great programs to, hire a lot of Canadians and put them into the shipbuilding industry, train them, give them the opportunity, and really, allow them to grow and grow their skills and abilities and be part of this industry within Canada. And then economic impact. So part of the National Shipbuilding Strategy, like I said, it supports our local workforce. So since 2015, we've had over 2,100 employees hired, 316 trades apprentices, 185 of those have graduated to become Red Seal certified tradespeople. We've had over 80 apprentices come through the Pathways to Shipbuilding program, and then over 150 students of various universities and within the Atlantic provinces were placed in a co-op program to do a 4-month co-op work term with the shipyard and gain their experience while they're in university. And then we've also invested over $19 million in skills training, leadership development, safety awareness, and lots of other training opportunities as well. So that's a quick, very high-level overview of the shipyard itself and Irving, and where we stand and things that we're able to do as part of the National Shipbuilding Strategy. So now let's dive into the Harry DeWolf class vessels and talk through some specifics about that platform. So great picture here of the future HMCS Margaret Brooke. This was her just last month in her May sea trials, coming back into approaching the Halifax Harbor. So great to be able to get her out there for that and conduct a successful sea trials. So the Harry DeWolf and AOPS platform, just over 100 meters long, 19 meters wide with a 6,600 ton displacement. It's rated for Polar Class 5, so it basically means it's designed for operating in medium first-year ice conditions with full 10/10 ice coverage in Canada's Arctic. It has accommodations for up to 87 people, and as well, it's a very versatile platform. So as you know, we conducted Arctic trials and then subsequently tropical trials. So the vessel is designed for air temperatures down to minus 29 degrees Celsius up to plus 35 degrees Celsius. So like I said, very, very versatile for our Canadian waters and even down to the Caribbean and the Mediterranean. And as well the seawater temperatures. So it's designed for minus 2 degrees Celsius seawater up to plus 29 degrees Celsius. So it's really, really designed for, the great extents of, Canada's waters that we have around here in the Maritimes, as well as on the West Coast. We have the Atlantic Ocean here, we have the Labrador Sea, the Davis Strait, all great areas that are very, very cold and have very harsh environments. And then we have the West Coast, which can get quite warm in the summer, and as well it provides a great platform for any other missions, humanitarian missions in the Caribbean for, say hurricane relief support. The vessel itself, very versatile and very capable within all those different areas. So as for power generation and propulsion, so we got some great pictures coming up here of a blog post from Sandy McLaren. I'm sure some of you have seen that blog post. So the ship's power generation, it's a diesel electric power and propulsion system. So we have two main engine rooms in the ship, which are fully redundant. Each engine room houses two main diesel generators supplied by MAN, each of which is capable of producing 3.3 megawatts. In addition, we also have a 1.3 megawatt emergency or harbor generator as well. So that can be used in a combination of either of those statuses. So it can be used if you're at anchor in the harbor and you don't need to run a main propulsion generator to provide electricity to the ship. You can run a smaller generator to help with fuel economy, other things if you're at anchor in port. She also has two 4.5 megawatt propulsion motors and 1 megawatt bow thruster. So all of which are designed specifically to operate, in the ice waters that we put the vessel through for testing during Arctic trials as well. As for deck equipment, so this is a great photo of the on the bow area of the enclosed and heated forecastle. So it provides a great sheltered environment. It houses all the line handling equipment for the mooring winches. It houses our anchor windlasses, towing equipment, provision davits, and just provides a really, really great sheltered environment when you're operating those harsh environmental conditions for the crew to be able to work safely and comfortably. So we were able to test a lot of the equipment in this compartment when we were up north. And the compartment, like I said, it provides great shelter, maintains a great temperature, very comfortable, and a great environment to work in. Off the stern of the vessel, we have the quarterdeck. So this area it looks small, but it houses a lot of equipment. So on the back, on the aft port side of the vessel, we have the 20-ton main crane, capable of loading sea cans from the pier onto the ship, capable of launching and recovering the landing craft, which is right in the middle of the picture here, as well capable of picking up any versatile equipment such as pickup trucks, ATVs, snowmobiles, anything like that for loading them out to the vessel. The quarterdeck also houses the 3-ton auxiliary crane, which is in the aft starboard corner, and as well, there's a small Zodiac there, which the 3-ton auxiliary crane can be used for launching and recovering it in the aft starboard corner of this picture as well. The other thing that you see in this picture is a sea cam on the right side. So the quarterdeck, not only can it hold and properly secure for the sea cans onto the quarterdeck, it can support them electrically, mechanically for any equipment that you can place in a sea can. Whether you need that for extra accommodation spaces that can be accommodated with potable water, black and gray water services, electrical services, compressed air services. So anything that you can put in a sea can for research facility, accommodation facilities, additional tooling and equipment to support the mission at hand. This vessel Harry DeWolf can take that equipment, store it safely, and protect it on the quarterdeck, and service it properly to complete the mission at hand. Another thing that you don't see in this picture, actually, just behind where the camera is, there's a vehicle garage as well. So it's a small garage which can house various ATVs, snowmobiles, pickup truck, anything at all that you need to load out to this vessel to support the mission at hand. It can hold it. So small area of the vessel, but there is a lot of versatile equipment in this area to make the ship successful. Carrying on with deck equipment, a great photograph here of the ship's flight deck and hangar. So flight deck and hangar to support the CH-148 Cyclone helicopter. I believe Harry DeWolf just in the past month or so has actually been completing her shoal trials for, they've successfully landed a helicopter on Harry DeWolf, and are now going through, I believe, the fueling operations and testing for shoal certification. Also, what we see in this picture, we have the port and starboard enclosed lifeboats, which can be launched both under emergency power or stored hydraulic power if necessary. And of course, them being enclosed makes them very, very much necessary for the Arctic environments if, heaven forbid, that you have to use those. And on the deck above, where the lifeboats are currently stored in this picture, we have additional life rafts, which can be launched and used for emergency purposes as well. So there's a lot of great versatile deck equipment packed onto Harry DeWolf, and as well we have the two multi-role rescue boats and davits as well, one port, one starboard. It's a great picture here from our sea trials on Harry DeWolf, training our sea trial crew for launching and recovering the rescue boat. And again, great tool for personnel transfers. We use them quite a bit with a few times I've sailed with the Navy post delivery on Harry DeWolf for transferring personnel both to the ship and ashore, and as well for rescue missions, search and rescues, personnel overboard drills. Very versatile davit, which again can be you can use the davit to launch the rescue boat through the emergency power on the vessel from the emergency switchboard, or as well through stored hydraulic power. So very versatile, very redundant to be able to provide that equipment to the ship. Now getting into the interior of the vessel. So accommodation spaces on Harry DeWolf are very, very comfortable. I would say they're much more spacious than what I think some of you might be used to in previous naval ships. So we got a great view here of the commanding officer's day cabin, office area on the left there, and as well as lounge or meeting area on the right as well. So a lot of cabins on the vessel are open like this. They're very comfortable. Lots of open space, lots of headroom, and just provides a great comfortable platform for those folks spending a lot of time at sea. As well, what we have is the picture on the left here on the bottom, the all ranks cafeteria. So not typical, I guess, for a Navy vessel to have all ranks, everyone from master sailor and below, right up to the commanding officer, eating in the same cafeteria. But from what I found sailing with Harry DeWolf and her crew provides a great, comfortable, and open atmosphere to sit down, share a meal with all of your ranks, and share conversations and stories throughout that voyage and throughout that deployment. Obviously, of course, they still have access to their rank-based lounge areas, the Master Sailor and Below Lounge, Chief and Petty Officers Lounge, and the wardroom as well. So that is split up to provide them that leisure area based on their rank. But I think the all ranks cafeteria definitely provides a great eating and socializing area for the vessel. Petty officer's cabin shown on the right here, just an example of how open and spacious these cabins are. Typically 2 bunks in this type of cabin, lots of headroom, and each cabin has its own dedicated shower unit and headspace as well. So very comfortable to stay in. Accommodation spaces that I've stayed in while sailing on these vessels are, extremely quiet, very comfortable, and just provides a great atmosphere and a great place to stay when you're at sea for the extended periods of time that our Navy is. Moving up to the bridge area of the vessel, so very wide open, very large bridge in comparison to a Halifax class frigate, with a lot of equipment packed in there. So a picture on the left here with Commander Gleason on the starboard bridge wing console. Provides thrust control, propulsion control, navigation data. One of those bridge wing consoles, both port and starboard of the bridge. And then we have the picture on the right showing all the equipment across the front area of the bridge. So all your navigation equipment, control room status, propulsion status, and propulsion controls and steering helm. So all held up there. What you don't see in this picture is on the aft end of the bridge, there's actually a machinery control console and damage control incident board. So provides the capabilities for either a rep from the engineering department or someone from the bridge team to have access to any piece of equipment that you can control from the machinery control room, you can control and monitor from the bridge. So very versatile in that sense. when we were conducting Arctic and icebreaking trials, I would be monitoring the main diesel generators, the propulsion shaft line, the thrust control, and all of its auxiliary support systems: fuel, lube oil, air, cooling water, absolutely anything that I needed to monitor to ensure the ship was performing as per its design conditions. I was able to monitor from the bridge. And what that allowed was a great um, list of information to be able to talk through any questions that the bridge crew had while they were getting a feel for how the vessel would perform in those Arctic and ice conditions. So it just provides, like I said, very versatile, provides a level of access to that control and that information within that area to be able to, have that coordination and communication between your engineering team and the bridge team all in that same area, as well as conduct damage control exercises, the entire build system, fire main system. Like I said, any system that can be operated from the machinery control room can also be operated from this console on the bridge as well. So that's Harry DeWolf class and platform overall in a nutshell. Very high level view there. Obviously, there's lots more details that we could get into, but I'd like to talk a little more about the Arctic Trials program specifically and the icebreaking program as well. So really, the goal that we had set out with the Arctic Trials program was to demonstrate and test the vessel's ability to operate in Canada's northern waters. So the requirements for the design were, like I said, an air temperature of minus 29 degrees Celsius and a water temperature down to minus 2 degrees Celsius. The ice conditions that we were looking for is first year ice up to 1 meter thick and 500 kPa of ice strength to ensure that we were testing the hull against the design criteria of the vessel. So the program was broken down into two main categories: icebreaking trials, which included a 1 nautical mile speed run where we test the vessel's ability to proceed through its design ice conditions and at what speed can it progress through the ice during those conditions. The star maneuver test, which is a test built to really determine how maneuverable the vessel is in these ice conditions and to make sure that when it gets into these conditions, it can properly turn around, it can back out, it can navigate as it needs to, no matter what condition it is in. We also completed a 4-hour, 100% power endurance run based on the propulsion system to make sure the hull and the main diesel generators and the propulsion system and the shaft line are able to cope with the Arctic conditions and the ice conditions. So that includes everything from ensuring the correct cooling water temperatures to your main diesel generators, to ensuring that the propellers and shaft line can handle the ice impacts and the ice milling that you'll be able to put those through during that time. And we also completed a vibration survey to ensure that when you put the vessel in these ice conditions, there is obviously a lot of vibration, a lot of noise, make sure everything is fastened correctly, everything is mounted correctly, and can withstand those conditions. And then we look at the Arctic trials, where we tested everything from deck equipment in the cold atmosphere to the HVAC system and its ability to keep the ship warm, comfortable, keep fridges cold, and to the de-icing system. So to be able to keep decks clear and free of ice, be able to keep any emergency escape routes, doors, hatches, all of those free from large accumulation of ice in these cold conditions. We also completed another 4-hour, 100% power endurance run in open water at cold temperatures, and then tested any exterior auxiliary and electrical systems. So any mechanical systems used to fuel lifeboats, rescue boats, the landing craft, the cranes, any other equipment that you can think on the exterior of the ship, any communication equipment, we test that to make sure it can operate properly as per design in these cold conditions. So our Arctic Trials team consisted of 5 of us representing Irving Shipbuilding. So we had Trevor Seymour. He's an HVAC engineer with Irving Shipbuilding. A lot of past experience, a lot of history with the project. Has been on it for the AVS project longer than I have. So he's got a lot of great experience and exposure to the design of the HVAC system and really lended a wealth of knowledge during the testing in these cold conditions. We also had Mitchell Pleat, as well as an HVAC engineer with Irving. He's relatively new to the project, but some great experience in other projects throughout Canada, and was certainly an asset to bring on Arctic trials with us. We have myself, as I said, I'm a test and trial specialist for mechanical, looking after machinery auxiliary systems, propulsion systems, and power generation. We had Rob Davidson. He's our test and trials electrical specialist. Rob has a wealth of knowledge as well on various electrical projects throughout Canada, and is able to tackle any piece of electrical equipment to make sure that it was operating properly, and if it wasn't, to fix it and make sure it did operate correctly in these conditions. As well, we have Raymond Creaser. He's the naval architect for Irving Shipbuilding. Has been on this project longer than anyone else we took on our Arctic trials, and he's been around since the model testing of AOPS. Been involved with the hull, the propulsion system, the ship's inclining experience, and as well just able to lend quite a bit of knowledge towards the vessel design, the hull design, and how it's expected to perform in these ice conditions. So Arctic trial route. So we left Halifax and we departed Halifax Harbor on, I believe, the 9th of February of this year. It was about a 9-day transit to our trial window, which you see is in the upper end of this picture here between Baffin Island and Greenland. Once we arrived there to our test area, that gave us 5 days of Arctic and ice-breaking trials, followed by a 9-day return transit to Halifax. So really, it felt like quite a bit of time in transit to leave from Halifax and get to our test area, but really it gave us a great window of opportunity to work directly with the ship's crew, make sure that if there were systems that they had questions on, they weren't sure about, or they just needed help to troubleshoot or repair, we were able to help and lend hand in that area. And then as we started progressing further north and got into colder waters and colder environments, we were able to start doing preliminary testing on everything that we would then have to officially test in the cold weather and the ice conditions. So everything from the HVAC systems to crane systems, boat systems, to doing checks on the propulsion system and how it's expected to perform in ice. We were able to conduct preliminary testing, weed out any bugs in the system, and get it operating properly to ensure that it was ready for its testing once we got to the Arctic and ice areas. So on the next few slides, I've got just some great pictures of the areas that we transited through on our way to the test area in the Davis Strait. So obviously we leave Halifax, and the first place we encounter is the Newfoundland Grand Banks. So we got into some lovely weather going through there, about 6 to 7 meter seas, and as you can see the picture here on the quarter deck with the landing craft secured down and the billy pew, the cranes. Everything held up very, very well and was properly secured for sea for that. So kudos to the crew for making sure of that. And as well, this weather also gave us opportunity to really put that active fin stabilizer system to the test. So what it does is, as long as you're proceeding at, I believe, above 6 knots, the vessel can have the fin stabilizers deployed. It'll actively tilt and rotate those to provide drag and lift on either side of the vessel to help keep her stable and upright. Harry DeWolf is a flat bottom vessel, so it does have a tendency to roll and bounce quite a bit, obviously, more so than a Halifax frigate, but I'm told it's not nearly as bad as the MCDVs, so that's we'll take that as a positive. Yeah, so putting her through this weather, she handled really, really great, I must say. And being as exposed as that quarterdeck area is, it really showed how well all that equipment can be latched down there and how well it can be secured. So definitely a great test in and of itself to put the vessel through. As we proceeded north from Newfoundland, we got into the Labrador Sea, which was just an absolutely beautiful area. I mean, you can see here, this was the vessel's first encounter with some sea ice. We called it, they're referring it as pancake ice. So it really just looks like little lily pads of ice formations out across the sea. And you can really tell there how, when you have the presence of that, it calms down any ripples or waves on the water and just gives an absolutely beautiful scenery to look at. So this was as we were proceeding north, getting further and further away from any vessels around us. I believe there was a few fishing vessels in this area, but that was it. It was just Harry DeWolf, proceeding north. So as we were traveling up the Labrador Sea, the navigation officer and the Met Tech, they were tracking all sea ice extents, and what we would expect to get into, what kind of weather, freezing spray that we might be getting into, and as well tracking where we expect to find the design ice conditions on to be able to properly test the vessel. So every day they would track that, provide an update, and them and the commanding officer would adjust their plan accordingly, adjust their course to get us to the proper testing area, which was in the Davis Strait. And as well, just another great picture here of the Labrador Sea. Some beautiful icebergs in that area as we proceeded further north. I just got into a bit more of ice in the area, icebergs such as this, and just some absolutely beautiful scenery. And like I said, then that brings us to the Davis Strait, so the test area for the vessel. So basically, as we started approaching into this and get into some heavier and heavier ice concentrations, that really gave the bridge crew and the commanding officer and his team time to ease the vessel into it. Commanding officer, I believe the first night we encountered ice, he was on the bridge with his team until 5-6 a.m., making sure they were trained and comfortable, and had the skills and abilities and were comfortable in navigating the ship through the ice and just providing those great training opportunities. So, great leadership shown by him at that time. And so during that, we were able to do preliminary checks on the propulsion system, making sure that when the shafts and the propellers were encountering these ice formations, everything was responding accordingly, and make fine-tuning prior to getting into our final testing. So got some great little videos here of how the ship performed as it first started to encounter ice. So the video on the left is taken from the quarterdeck of the vessel. It's the one I'll show you first, and really gives you a sense of the ice formations that the ship was able to traverse through, and just the sound and the feeling of that during that. So I'll go ahead and play that, and then we can talk through a few things afterwards. And just let me know if you guys can hear the sound. As you can see, the ice areas that we were starting to navigate through, you start to see some ice formations turning up on the side right about this point. So this was ice that was probably just shy of 1 meter thick, and the vessel at this time was carrying through it with 3 of 4 main diesel generators operating, and it's just steadily able to continuously progress through this ice without any issue, without any vibrations, any noises. It's reasonably smooth, I must say. All right, and the next video that I have is taken from the bridge of the vessel. So this will give you a bit of a feel for how they are operating and controlling the vessel through the ice. She starts out going along on her port bow, a little bit of an ice ridge, and you'll hear a few commands for rudder changes to port to help drive the nose of the vessel into these ice formations, and you'll see how the vessel first starts out sort of gliding along that ice ridge, and then as they reorient the rudders to hard over to port, the vessel is really able to turn her nose into it and really start progressing through it. So we get a sense for how it responds to course changes in these ice conditions, and is able to push herself through these ice conditions. you can see at this point, she's sort of carrying along the edge of that ice ridge. They've just applied port 30 rudder, and in a moment you'll start to see the bow sort of drive into the ridge itself and start progressing through it. So as well, what you hear in this video is one of the bridge officers just stated that they were at 100%. What they're referring to is as they're going through this with all four main engines online, with the propulsion system, you're able to monitor the torque values on the shafts. So they're monitoring how much torque is being applied to the propellers, and towards how much thrust you're getting as the propellers start milling through these ice formations and pushing the ship forward. So that's just a couple of great examples there on how well the ship handles. Like I said, it's not, it wasn't very aggressive overall at all. Not violent, not heavy vibrations, nothing like that. She's very, very capable to be able to proceed through these ice conditions and make it into the area that she needs to go. So that brings us into the first part of the test, which was our icebreaking trial, so the speed run. So there's a little diagram on the right here, which shows basically what the test consisted of. So we bring the ship into a small ice channel, some close packed ice, or have her break her own channel into the ice. We take a sample of the ice itself, make sure it's the proper thickness, the proper strength, and then you start out with an approach run of the vessel to bring her up to speed. And then as you approach the unbroken ice, the intent is to bring the ship to full propulsion power, full thrust ahead, and then start to measure the speed over 1 nautical mile distance at which the vessel is able to progress through its design ice conditions. So like I said, ice conditions we were looking for were between 0.8 and 1.2 meters thick and greater than 500 kilopascals of strength. So the way we determined this, we were able to put our ice sampling folks onto the ice with the crane's billy pew. You see on the left there, they have a sentry watch out for polar bear watch. That's because the morning that we were doing this, these polar bears on the right were probably only 100 to 200 meters away from our folks out on the ice actually gathering these ice samples. So polar bears were hanging around us for about 24 hours. That's 2 of the 3 there. It was a mom and 2 cubs. So they were, very curious, walking around, hanging out, and very observant to everything that we were doing. So to get our core samples, like I said, we'd use the ship's 20-ton crane in the Arctic conditions, land the billy pew on the ice, have our core samplers get off onto the ice, drill a core. They drill 3 cores in every location, measure its thickness, measure its temperature, and use that properties along with the salinity of the ice to determine its strength, to make sure that the ice was proper thickness and proper strength to meet the design conditions of the vessel. So once we knew we were in the right area, we were able to start the test of the ice-breaking speed run. So this is a view off the stern of the vessel at the end of that 1 nautical mile run, where you start to see the channel of ice that the ship was able to break through. Just gives you an indication how well she breaks away that channel there and how well she was able to push through it. So then at the end of that 1 nautical mile run, what we needed to determine was make sure that the ice conditions were consistent along that entire mile. So we were able to start bringing the ship astern. Again, placed our sample team on the ice with the ship's 20-ton crane and billy pew, and they'd walk along that 1 nautical mile of broken ice path, and again, take core samples every couple hundred meters or so. Again, they're measuring thickness that entire time. So to give you an indication of ice thickness, the tool that they're using there to drill the core sample, that was just over 1 meter in length. The ice that we encountered for this test averaged about 0.9 to 1.0 meters thick. So just a little shorter than what the coring tool shown in this picture was able to accommodate. So once we collected all the data, we were able to put that information together and then assess the speed of the vessel with the ice conditions that we were put in. The vessel proceeded, well within its design criteria. At full propulsion power, I was able to, steadily increase its speed as it's breaking through those ice conditions, to the point that the commanding officer actually started to pull back on the throttles a little bit because he didn't want to proceed through the ice at too high of a speed. So just goes to show of how powerful the vessel is for these designed ice conditions, how well it's able to progress through the ice and get to the mission area that it's going to have to get to throughout its life. The next test for the ice breaking trial was the star maneuver. So the intent of this is if you're in a broken ice channel and you come up against an ice ridge or somewhere that you can't continue going ahead because the ice conditions are just inadequate, or you just need to turn around and go and change your heading. So the intent of this is to use full power at both ahead and then astern in varying directions and rudder angles to be able to break out of the ice channel that the ship is in, clear sufficient area around the vessel, and clear enough areas so that the vessel can actually turn around, change its heading, and go back out the way it came in. So the way we tested this, we found a great ice field here. This is the path looking off the stern of the vessel as we broke into that ice field and created that large ice channel. So you can see that even though we've created that channel, it is still completely filled with broken parts of ice and highly congested with ice as well. So you can imagine going astern in this, you start to get all that backing up against the stern of the vessel, starts to go down under the vessel, and really what the ship has as well to accommodate that is right above her rudders. Underneath the stern, she has large ice knives, which help to break apart these large chunks of ice so that they break apart, they split away from the rudders and away from the propellers to give the ship a better capability going astern. So next picture here, it shows going from right to left across the screen. You can see the previous channel that the ship was in, and then we were able to break out of that by applying full thrust ahead and hard over to port with the rudder to be able to dig the nose out of that ice channel and start breaking ice away to change the heading of the vessel. And once you get to this point, the bridge team would then start to bring the ship astern as well, slowly come up to full power, bring the ship astern into some unbroken ice, and start to pivot her nose in to change her direction, her heading. So then at the end of it, this is sort of what you're left with. You can see right in the middle, you've got a large open body of water and broken up ice. And then going off into the distance, you have the two other directions that the ship traveled in to break out of her channel and change her heading, both in a head and stern direction. So it was a great test to show, the capabilities of how the ship can maneuver in these conditions. If it has to, if you're proceeding ahead, like I said, you get to a large ice ridge, something that you can't progress through, you need a way to get out of that prior, other than just going astern. So this was a great test to be able to show the capabilities of the vessel in these conditions. So some environmental challenges that we got into with the ice breaking trials. So this was an interesting year in the Arctic for ice conditions. So really what we were looking for ideally was, like I said, 1 meter thick ice with a smooth, consistent concentration with the proper strength of ice. So this year we had a bit of a varying season, which caused the ice to sort of freeze in these conditions and then subsequently break apart and refreeze. So what you're seeing in this picture is one of the ice fields that we encountered that while looking for proper test ice, we come across a number of these where it's clearly ice that was, once solid, completely frozen together, has since broken apart and refrozen again. So what that causes with for test conditions was just inconsistent ice and hard to get proper data. So as you start to break through this, it splits, it causes fractures very easily, and it starts to break away and form large channels to break large pans and sheets of ice away from the vessel, which wasn't what we were looking for. So what we were able to do, like I said, the navigation officer and the med tech, every single day they were tracking ice conditions, ice quality, ice flow sizes, and locations and where we thought the best ice would be. So they were working day and night to find the proper ice area. I believe we spent upwards of of 3 days sailing around different areas, finding different ice flows, and putting our core sample team on the ice, taking core samples, checking it for thickness and strength to find the proper ice flows. So that was a challenge, but the strength of the ship's crew, the commanding officer, the navigation officer, and the med tech were outstanding in this case. They eventually brought us to the right area after a few unlucky tries to be able to put the ship through our design conditions. The other challenge that we had this year for the Arctic trial was air temperatures. So the graph on the right here is just a trend of temperatures from the day we left Halifax to the day we returned to Halifax. So you can see right in the middle there, we only had about 48 hours at cold temperature. So our requirement was to hit the design requirement of the vessel is minus 29 degrees ambient. The coldest we were able to find between Baffin Island and the Davis Strait was about minus 20 ambient with minus 35 to minus 45 wind chill. So not quite the area that we were looking for, but just kind of, it was interesting looking at this data afterwards and thinking through that, this is part of the reality of Canada's Arctic and how it's trending with different environmental changes and atmospheric changes. So it's good to know that as well that, with the conditions that we spent looking for, we had scientists and weather technicians working to plan the right time for the Navy to take this voyage. And we took it right in the middle of February, which is the coldest and the harshest time in these areas. And the ship performed outstandingly in the worst conditions that we were able to find for it. So that's a quick overview of the ice breaking trial. I'll get into a few specifics on the Arctic trial. So this is everything cold weather related, deck equipment, HVAC, de-icing systems, like I said, a full power endurance run, and any exterior and auxiliary electrical systems. So equipment that we tested, obviously our 20-ton crane, we use that almost every day in these ice conditions to pick up the billy view, load our team out onto the ice safely, conduct their core samples and retrieve them and bring them back to the vessel. So it just went to show, how resilient this deck equipment was in these cold conditions. Other things we tested, the lifeboat davits. We did a long-term recovery of the lifeboats in these cold conditions, the rescue boats, all the provision davits, the anchor, any external service connections, whether electrical or mechanical, to make sure that piping that has proper heat trace surrounding it is able to keep the pipe fluid inside it from freezing, to keep the pipe clear and operational, as well as the de-icing system. So there's large amounts of deck areas throughout the ship that cover all emergency escape routes, hatches, doors, ladders, handrails, everything that provide a small heated coil through those to keep those surfaces free of large ice accumulation or snow buildup. So in this picture here, you can actually see along the port side of the flight deck, that is one of the designed emergency escape routes. So that patch that is snow and ice free, that's because of the deck de-icing system that's directly underneath it to keep that free in the event of emergency, that you can get to the lifeboat or life raft or emergency stations safely and quickly. So with that, we were able to, like I said, we tested everything from the HVAC system to deck equipment to electrical systems in the cold weather. We were able to, with the HVAC system, we were looking for internal accommodation spaces, temperatures, humidities, everything to test, the ability for the ship to keep a safe and comfortable environment for her crew. And like I said, it performed outstandingly. So a few final thoughts that I have, really, AOPS as a platform and the Harry DeWolf class as a platform. It's built as, a versatile ship that's able to serve all of Canadian waters. So like I said, Harry DeWolf went through our Arctic trials in February. Shortly thereafter, in March, end of March and into April, she went on tropical trials and went down to Puerto Rico. So that is just about as far north as you can go in February, to about as far south to the most extreme heat conditions and seawater conditions. Just goes to show how quick a turnaround this vessel can go through for those differing conditions. Putting the ship through the ice breaking test. The feedback I got from the commanding officer, Commander Gleason, during that testing is he was very thoroughly impressed. He said the amount of power that the ship has to be able to progress through those ice conditions is tremendous. It provides the ship with the capability to go anywhere that the Navy can take it. When we were up between Baffin Island and Greenland, we were hundreds and hundreds of nautical miles away from the closest ship. It was an area that even the Canadian Coast Guard was not at that time of year. So to be able to take a first-class vessel with her new crew, new commanding officer on that vessel, and take her that far away from anyone else or any other support ships was, it speaks to the design capabilities of the vessel and what it can do for our Navy. The deck equipment on the vessel, like I said, there's tremendous amounts of capability on the quarterdeck, the flight deck, the hangar, the lifeboats, the rescue deck, the crane systems, just to be able to provide support to any mission that the ship can do, whether it's humanitarian, environmental response, search and rescue. The ship has the capabilities to put the appropriate equipment on board to make her mission successful. It's a new level of comfort and technology for operators and end users. Like I was talking about with the machinery control console on the bridge, gives live data, feedback, and control from an engineering officer who needs to spend some time on the bridge to, a member of the bridge team who needs to know a bit more specifics about the propulsion plant, what it's capable at that point in time, and to get real feedback. And as well, in the event of damage control, to be able to take control and monitor and operate any of those damage control systems from the bridge in the event of an emergency. As well, so we talked about the accommodation spaces, the all ranks cafeteria, and what level of comfort. And I kind of describe it as a bit of a community level. So it was an area where you go in for your meal, you'd sit down with anyone from the commanding officer to a master sailor and below, and just have a conversation, share stories about where they're from or how their experience is going, their career, their jobs, whatever it is, and just created that a great open atmosphere and a sense of community amongst the crew. And then talking about the ship's capabilities for power and redundancy, so it meets the Lloyd's PSMR star requirements for redundancy of machinery control, damage control, and her ability to take a damage control incident and return to port safely. And then it's diesel electric propulsion system, very highly efficient. It meets Tier 3 emission standards so that it can operate efficiently and environmentally friendly, we'll call it, in these Arctic conditions. With those ever-changing maritime emission restrictions that are coming into place, the ship has Tier 3 capabilities right now. And, its level of efficiency, it has 4 3.3 megawatt generators, but the vessel still has a range of over 6,800 nautical miles, traveling consistently at 14 knots. So overall, a very, very capable vessel for our Navy and for our Canadian waters. And then if we look at as well, sort of my little overview of the national shipbuilding strategy and what it's able to do for Irving, for Nova Scotia, and for Canada. So Irving's committed over $400 million in facility investments, which has provided numerous opportunities for jobs, training opportunities from everyone from trade workforce to people like myself. I'm only, like I said, I graduated from Memorial University 4 years ago, and this year I was able to take part on a first-class Arctic and icebreaking trial with the Canadian Navy. So being able to develop the expertise in our young workforce, in our Canadian workforce, and provide those training opportunities to then be applied into the Type 26 CSC project, I think is tremendous for our province here in Nova Scotia and our industry Canada-wide, really. So overall, I think great experience from my side. Very pleased with Harry DeWolf as a vessel, and I believe the feedback from the Canadian Navy throughout all the post-delivery testing has been tremendously positive as well. So with that, thank you for your time. Much appreciated. I'll hand it over to Barry now, and we can open up for a bit of a Q&A session and discussion on any questions that you might have.
Wow,